Hello and welcome to Science Visualized. Today we're looking at substitution versus elimination reaction. If you're given an alkyl halide, say a primary alkyl halide, where we have a halogen there, X, and that X could be chlorine, bromine, iodine, or fluorine, then that alkyl halide can react with a nucleophile, and you end up with what's called nucleophilic substitution, where the nucleophile will replace the halogen, and therefore you end up with the same alkyl group, but now the halogen has been replaced by a nucleophile. This reaction can proceed in two ways. So there are two different mechanisms. The first one is called SN1 reaction, and the other one is called SN2 reaction mechanism. So SN1 is substitution nucleophilic unimolecular, while SN2 is substitution nucleophilic bimolecular. Unimolecular means that the rate of that reaction depends only on the concentration of the alkyl halide, and we call that the substrate. So the rate of the reaction depends only on the concentration of the substrate. On the other hand, the SN2 reaction is substitution nucleophilic bimolecular, and bimolecular means that the rate of the reaction depends on both the concentration of the substrate and the nucleophile. So that's where we get bi. So it depends on both. It's a second order reaction. Now there are some key differences between SN1 and SN2. So I'll go ahead here and list SN1 and SN2 mechanism. Number one, if you look at the solvent, SN1 requires what we call polar protic solvent, while SN2 is polar aprotic solvent. Now, protic means that that solvent donates a proton or hydrogen ions, while aprotic means that the solvent has no hydrogen ion that can be donated. The reason for that is that SN1 involves what we call carbocation intermediate, as a positively charged intermediate, while SN2 no carbocation. So using polar protic solvent will stabilize the carbocation intermediate, and it will also help stabilize the nucleophile, and the nucleophile can be a negatively charged nucleophile. Because the rate of the reaction only depends on the substrate, then that means that the reaction is faster when you have polar protic solvent, because that will stabilize the nucleophile so that it doesn't react quickly with the substrate, while at the same time allowing the separation of the halogen from the alkyl group. So it allows or stabilizes the formation of the carbocation intermediate. Number one is solvent. Number two is carbocation intermediate. Number three is substrate. Alkyl iodides will react faster, followed by alkyl bromides, followed by alkyl chlorides, and then followed by alkyl fluoride. And that's the same thing also for SN2. The reason for that is because if you look at the carbon-iodine bond, that bond is long. So you get a long bond where the bond is polarized, where the positive end is towards carbon and the negative end is towards iodine. Because the bond is highly polarized, it makes it easier to break the bond. Same thing with SN2, it will involve breaking the carbon-halogen bond at some point. Fluorine, on the other hand, is the strongest electronegative element, meaning that the bond between carbon and fluorine is really strong, meaning that it will require a lot of energy, a higher activation energy to break that bond, and that will make that reaction slower. So this is actually what we call the nature of the living group, number three. Number four is substrate. And here we're looking at primary, secondary, or tertiary alkyl halide. For carbocation formation, remember SN1 goes through carbocation. Tertiary carbocation is the most stable. So carbocation, tertiary is the most stable, followed by secondary, which is much more stable than primary, which is more stable than the methyl carbocation. So basically you never form primary or methyl carbocations, and that means that SN1 reaction will prefer tertiary alkyl halide. We see the reverse for SN2 reaction because that will be faster in methyl, so that's SN2, and then followed by, so you start with methyl and then followed by primary, and then much more faster than secondary, and then tertiary never goes through SN2. The reason for that is that in tertiary substrate, so if you have something like this, chlorine, so that's first alkyl group, second, and 3. So that's a tertiary alkyl chloride. You'll see that this carbon that has chlorine is really crowded. And in SN2 reaction, you want the nucleophile to approach that carbon so that you can kick out the chlorine. But because you have 3 alkyl groups around the carbon with the chlorine, it makes it crowded and harder for the nucleophile to approach. That's almost like if a bank robber wants to approach a bank, and that's where the gate is, or the door for the bank is, and you have 3 police officers, number 1, number 2, and number 3, then that door is more crowded and heavily guarded compared to a door that only has 1 police officer, so that would be primary. And that makes it easier for the nucleophile to approach the primary alkyl halide. So based on that, we will say that tertiary is faster for SN1, and this will be an example of tertiary alkyl fluoride, while on the other hand, primary alkyl fluoride will be faster for SN2. Now it gets really tricky when you're looking at secondary substrates, because in that case, both SN1 and SN2 are in competition. And then you have to look at other things, and that's where things like solvent will come into play. So if you have polar protic solvent and a secondary substrate, then that will be SN1. If you have polar aprotic solvent and a secondary substrate, then that will be SN2. Thank you very much. Please stay tuned. We'll be talking about the mechanism of SN1 and SN2, and later on we'll also talk about elimination reactions, E1 and E2. If you enjoyed this presentation, please support the channel by subscribing and also liking this video.